Hello and welcome everyone. So in this video, we are going to discuss the seventh chapter, that is transactions from designing data intensive applications. So let us begin. Let us first understand that why we need transactions. What can go wrong in data systems? So let us see different things. So the first one is that database software or hardware may fail at any time even when we are in the middle of writing some data onto the database, or any application can crash at any time. Also, there can be interruptions in the network. There can be many clients writing concurrently to the same database at the same time, and they can override each other changes. Also, some client may read data that is partially updated, giving an inconsistent view of the data. Also, there can be many race conditions which can cause bugs. So, in order to be reliable, a system has to deal with these faults, and it has to ensure that it does not cause any failure of the system. So, implementing the fault tolerance mechanism, we use transactions. So, transactions is a way for an application to group several reads and writes together into a logical unit. So, if we see that all the reads and writes in a transactions are executed as one operation, so either the entire transaction will succeed, that is, it will be committed, or it will fail, that it will be aborted or roll back. So, if it fails, then it is up to the application that it can safely retry. So, with the transactions, error handling becomes much easier for the application because it does not need to worry about the partial failure that some data has been updated or some has not been updated. So, the transactions is basically to simplify the programming model for an application which accesses the database. So, by using the transactions, the application is free to ignore some potential errors and concurrency issues because the database takes care of them instead. But not all application needs the transactions. Some applications might be more advantageous if they follow less transactional guarantees or they abandon them entirely. So how do we figure out that whether we need transactions? What all guarantees does a transaction gives us? So let us see. So the guarantees which transaction provide is known as asset properties: atomicity, consistency, isolation and durability. So let us first understand what is atomicity. So in context of asset, atomicity describes what happens if a client wants to make several writes but a fault occurs after some of the writes have been processed. For example, consider that you are writing some data to a database and the disk becomes full, or the network connection goes down, or some constraint like foreign key constraint or some integrity constraint is violated. So, if we consider that all the writes are grouped together into an atomic transaction and the transaction cannot be completed due to a fault, then the transaction will be aborted and the database must discard or undo any writes it has made so far in the transactions. So, what would happen if there would be no atomicity? So, in that case, a client would not be able to know that which changes have been written and which haven't been. So, application, if you want to try again, there would be risk that same changes would be applied twice. Thus, we have to ensure that there is some idempotency maintained. So in that case, if the transaction is aborted, then the application can be sure that it did not change anything, so it can safely retry. So that's why atomicity is important. Let us now understand what is consistency. So consistency is like maintaining the good state of a database. So we have certain statements which are invariants, or you can consider that some constraints that always holds true. For example, in an accounting system, the credits across all the accounts must balance with debits across all the accounts. So if you think deeply, the consistency is not the notion of a database, it's the application notion. So it's the application's data responsibility to define how the transactions will behave correctly and how they should preserve the consistency. So this is not something that database can guarantee. It is up to the applications, because different applications can have different constraints, which always holds true. So if you write bad data that violates your invariance, the database will not stop you. So although the database can take care of foreign key constraints or uniqueness constraints, but in general, the application defines what data is valid or invalid, and the database only stores it. So now let's see what is isolation. So most of the databases are accessed by the clients, that is by several clients at the same time. And that is no problem if they are reading and writing the different parts of the database. But what if they are accessing the same record, the same row, the same data at the same time? So we can run into concurrency problems. So in the context of asset properties, isolation means that concurrently executing transactions are isolated from each other so that no one is aware of each other's presence. So it is also considered as serializability, which means that each transaction can pretend that it is the only transaction which is running on the entire database, and the database has to ensure that when the transactions have committed, the result is same as if they had been run serially. But in practice, serializable isolation is rarely used because it carries some performance issues, whereas some databases use snapshot isolation, which is a weaker guarantee than serializability, and which we are going to discuss in the later section of the video. Now let's see durability. So the purpose of the database system is to provide a safe place where the data can be stored without losing it. So durability is the promise that once transaction has been committed successfully, any data will not be lost even in case of hardware faults or database crashes. So in case of single node database, durability typically means that data has been written to a non-volatile storage such as hard drive or an SSD. Whereas in cases of replicated databases, durability means that data has been successfully copied to some number of nodes. In order to provide the durability guarantee, a database must wait until these writes or replications are completed before reporting a transaction as a successfully committed. So just now we saw the asset properties. So in asset properties, we learned that atomicity and isolation describe what the database should do if a client makes several writes within the same transaction. So atomicity defines that if an error occurs in the middle of some writes, then the transaction should be aborted, and any writes that has been made up to that point would also be discarded. And isolation states that concurrently running transactions should not interfere with each other. For example, if one of the transaction makes several writes, then the another transaction should see either all of the writes or none of the writes, but not some subset of those writes. So as you can see that these definitions, atomicity and isolation definitions, assume that we want to modify several objects, that is records, rows, documents at once. So database takes care of single object as well as multiple object operations. So in single object operations we just modify one row, but in case of multiple object operations we modify multiple tables, multiple rows at the same time. So how do we identify that multiple read and write operations belong to the same transaction? So in relational databases, all the statements, everything between a begin transaction and a commit statement is considered to be the part of same transaction. But on the other hand, many non-relational databases do not have a such way of grouping operations together. So now let's see how this atomicity and isolation is used in case of single object writes. So let's consider we are updating a 100 KB JSON document to the database. So let us consider some scenarios. What happens if a network connection is interrupted? Does the database stores half of the JSON, that is, let's suppose 50 KB JSON, and the 50 KB JSON is not saved? Does that really happen? Or if the power fails in the middle of overwriting the previous value on the disk, so does we end up with old and new values spliced together? What happens if one of the client is updating the value and another client sees the partially updated value? Does that really happen? So to avoid these issues and to handle these issues, atomicity and isolation are used on the level of a single object, that is on the level of key value pair on one node. So atomicity can be implemented using a log for crash recovery, and isolation can be implemented using a lock on each object, where we are allowing only one thread to access an object at any one time. So these single object operations are useful as they can prevent lost updates when several clients try to write to the same object concurrently, but they are not the transactions. Basically, a transaction is usually understood as a mechanism for grouping multiple operations on multiple objects onto one unit of execution. So let us understand now, why do we need multi-object transactions? How multi-object transactions is different from single object transactions. We just learned that multi-object transaction means when we are updating multiple rows, documents or records at the same time in the same transactions. So many distributed data stores have abandoned multi-object transactions because they are difficult to implement in case of the partitions. But the question arises, why do we need multi-object transactions at all? Can we use single object operations only? So let us see some of the use cases where these multi-object transactions are used. So the first case is, so in relational data model, a row in one table has a foreign key reference to a row in another table. So multi-object transactions allow us to ensure that these references remain valid when we are inserting the data into the database. The second point is, in a document data model, the fields that need to be updated together are often within the same document. So that is treated as a single object document, and it is treated as a single object transaction, and no multi-object transactions are needed when we update a single document. But the document databases which lacks the join functionality encourages the denormalization. And when denormalization information needs to be updated, we need to update several documents in one go. So transactions are very useful in this situation to prevent denormalized data from going out of sync. The third case is in database with the secondary indexes, the indexes also needs to be updated every time when we change a value. So these indexes are different database objects from a transaction point of view. For example, without the transaction isolation, it's possible for a record to appear in one index but not in another because the update to the second index hasn't happened yet. So such applications can be implemented without transactions, but the error handling becomes much more complicated without the atomicity and lack of isolation. And these problems and these lack of isolation and atomicity can cause concurrency problems. So we saw that the main feature of a transaction is that it can be aborted or it can be safely retried if an error occurred. So we will not end up in a state where half of the data has been written and half of the data has been discarded. So let's see how we handle errors and aborts when we use transactions, and are they really perfect, or what issues occur while handling these transactions. So let us consider the first case. What happens if a transaction actually succeeded but the network failed? That means the connection between the server and client broke and the server was not able to tell the client that the call was successful but the database has been successfully updated. So in that case, the client would retry again and it would cause the transaction to be performed twice. So we should handle this idempotency in the application layer. So what happens if the error is due to an overload, and if we retry the transaction, it will make the problem worse. So in these cases, we should avoid such feedback cycles and we can limit the number of retries, so and can use exponential backups and can handle overload related errors differently from the other errors. The third point is it is only worth retrying only after a transient error and not a permanent error. So, what are the transient errors and permanent errors? The transient errors are like deadlocks, isolation violation, temporary network interruptions, or the failover. But permanent errors like constraint violations should not be retried because they would again result in the errors. So, if two transactions do not touch the same data, they do not update the same row, then they can safely run in parallel mode because neither of them depends on each other. So, concurrency issues only come when one transaction reads the data that is concurrently modified by the another transactions, or when the two transactions are trying to simultaneously modify the same data. So, concurrency bugs are hard to find by testing because these are generally the timing issues and they occur very rarely and also difficult to reproduce. So, in large applications, we don't even know that which piece of code is accessing the database at the same time and when it can access. So, databases have tried to solve this issue by providing the transaction isolation. So, transaction isolation pretends that no concurrency is happening. Basically, it tells that it is serializable isolation and all that it guarantees that the transactions have the same effect as if they ran serially. But serializable isolation has a performance cost and many databases does not want to pay that price, and it's therefore common for systems to use weaker levels of isolation which protect against some of the concurrency issues but not all of them. And those levels of isolations are harder to understand and also they can cause various issues. So now we are going to understand some of the isolation levels like read committed. Read committed is the most basic level of transaction isolation and it makes two guarantees. The first one is that when we are reading from the database, we will only see the data that has been committed. We will not see any dirty reads. Similarly, when we are writing to the database, we would only overwrite the data that has been committed. We would not make any dirty writes. So now let's understand in deep what are dirty reads and dirty writes. So let's suppose a transaction has written some data to the database but the transaction has not been committed or it gets aborted. So let's assume a user is trying to update a variable as x which is currently as 2 and he is updating it as 3. So if 3 does not get committed, so will the another user 2 will see the value 3 or it will continue to see the value 2 till the 3 is committed. So transactions running at the read committed isolation level must prevent dirty reads. So dirty reads mean that if a transaction is able to see the data from the another transaction which is still in uncommitted state, then that is called dirty read. So transactions running at the read committed isolation level prevents dirty reads. This means that any writes by a transaction only become visible to others when the transaction commits. So let's see why we need to prevent dirty reads. So the first point is if the transaction needs to update several objects. A dirty read means that another transaction may see some of the updates but not the other. So if we see this condition, then seeing the database in a partially updated state is confusing to the users and this may cause transactions to take the incorrect decisions. Now the second point is if a transaction aborts and any write that it has made so far has to be rolled back. And if the database is allowing dirty reads, it means the transaction would have seen those changes which have not been committed and later got rolled back. But in actual they do not get committed, so it gets confusing for the transactions and again it can take wrong decisions. So now let's move to dirty writes. So what happens if two transactions concurrently try to update the same object in a database? We do not know in which order the writes will happen, but we normally assume that the later write overwrites the earlier write. But What happens if the earlier write is a part of transaction which has not been committed yet and the later write overwrites an uncommitted value? So that condition is called a dirty write, and the transactions which run at the read committed isolation level prevents the dirty writes by delaying the second write until the first one has been committed or aborted. So let's understand why dirty write is needed. So let's consider a condition where we are updating the multiple objects in a transaction. And if we have such two transactions, then if the dirty write is allowed, then it can lead to bad outcome. And in the systems where consistency is very important, it can lead to an inconsistent system. So that's why dirty write is necessary. Let's understand how we implement the read committed. So read committed is a very popular isolation level, and most commonly database prevents the dirty writes by using a row level lock. So it means that when a transaction wants to modify a particular object, either a row or a document or a record, then it must first acquire a lock on that object, and it holds that lock until the transaction is committed or aborted. So it means that only one transaction can hold the lock for any given object, and if another transaction wants to write to the same object, it must wait until the first transaction is committed or aborted before it can acquire the lock and continue. So this locking is done automatically by the databases in read committed mode. Let's see how we prevent dirty reads. So one option would be the transaction which wants to read some object, it also acquires the lock on that object and release it again after it has read the data. So this would ensure that a read could not happen while an object has a dirty uncommitted value, because the lock would held by the transaction that has been writing. But this approach of acquiring the read locks does not work, because one long running write transaction can force many read only transactions to wait until the long running transaction has completed, and this would result in slow response time, and it is bad for operability. So most databases use another approach for dirty reads. So for every object that is written, the database remembers both the old committed value and the new value that has been set by the transaction, which is currently holding the write lock. So when the transaction is ongoing, any other transaction that wants to read the object simply is being given the old value, while when the new value is committed, then the transaction switch from the old value to the new value and it returns the new value. So that's how read committed is implemented. So let's summarize what we have covered in this video. So we have covered asset properties of the transactions. We have understood what can go wrong in the data systems and why do we need transactions at all. We have seen that a transaction might result in the single object writes as well as the multi-object writes, and how the atomicity and isolation helps in the multi-object writes. Then we have seen the weaker isolation levels and serializable isolation. Then we have seen the read committed isolation level and how they prevent dirty reads and dirty writes. And we have deep dived into dirty reads and dirty writes and why they are needed and why they are important. I hope you like the content. So far you have understood the transactions and why they are needed. In the later sections of this chapter, we are going to cover snapshot isolation, serializability, and two-phase lock commit. Please hit the bell icon and subscribe to my channel if you like the content. Thank you.